Hello. In this video, I want to talk about Newton's gravitational law. Newton's gravitational law basically says if you have two masses, any two masses, no matter how big or how small they are, there will always be a gravitational pull between them, a gravitational attraction between them, okay? So if I have a mass, let's just symbolize it by a block. Here's another mass here with another block. They are not necessarily, they don't necessarily have the same mass, right? We'll call that mass 1 and mass 2. And let's suppose that they are separated by a distance between their centers. We're going to call that distance r. Then there will be a gravitational pull. What that means is that there is a tendency for the two masses to come together and stick together, okay? And this gravitational pull can be calculated by a formula. We call it the Newton's gravitational law. This formula basically says the following. So we have F for force. So in other words, let me go back to those two masses here. So there will be a gravitational force or gravitational pull like this. That's the force F on both of them, okay? And this F, let me just put it down here. This F is equal to the product of the two masses. What that means, let's say this mass is M1 and this mass is M2. This is like measured in, say, kilogram. That will be a common unit for it. So there will be the product of the two masses, M1 times M2, divided by the distance between their centers, r squared. The distance between, I wanted to say the distance between the centers squared, up to a constant we call g, big capital G. This g, we call it the universal gravitational constant. Universal gravitational constant. And it has a specific value. G is equal to 6.67 times 10 to the negative 11 Newton meters over kilogram squared. You can also find this the formula as well as the constant in the formula sheet that is in our class, the one I developed for you. If you open it up, it's right here. Please be familiar with this formula sheet. So the right side of the formula sheet right here is basically the constants and their values, constant name and the value of that constant. So for example, for the value of G, the gravitational constant is right here. Can I make it bigger? There we go. Okay, so here it is. The universal gravitational constant right there, whoops, so here, 6.67 times 10 to the negative 11, and it's written in a different equivalent unit, okay? And then Newton's gravitational law is right at the bottom, if I remember, because there it is, right there. Right here, F equals G M1 M2 over R squared. I'm using capital R here, but that's basically what it is, equation number 17, okay? So how do we use this law and why is it important? I'll show you. Suppose, for example, I want to apply this law to two examples. And one example is, suppose that we have two people, all right? So here is the floor or the ground. And suppose we have two people. Here's one person right here and another person right here. There we go. And suppose that they are separated by a distance. We're going to call it R. I'll come back. I'll give you some numbers later. And let's say that this person, I'm going to call it M1, the mass 1, and mass M2. Let's suppose that M1 is, let's say, 90 kilogram, the mass of this person. This person, let's say M2 is, let's give her 60 kilogram. Okay, there we go. And so what we want to calculate, oh, sorry, let's say that the distance between them, let's make it R equals 2 meters. So there are two people standing in front of each other, 2 meters apart. That's about 2 yards. 2 meters apart. One person is 60 kilogram, the other person is 90 kilogram. According to Newton's gravitational law, this law right here, according to this law, that we can actually calculate the gravitational pull between the two people. Okay, in other words, there's a tendency for the two people to come together because as long as you have mass, you have gravitational pull. So we can calculate that. So let's do the calculation. So apply the law. So I'm going to put in the law. So F equals G m1 m2 over r squared. And I'm going to plug in all the numbers. So first, you always start with the symbolic equation, the equation in symbols. And then you always write vertically. You know, you don't write to the side here. Always write downward, okay, vertically. Not like English, we write from left to right. In mathematics, you kind of write vertically, okay? So the next step now, you want to plug in your numbers. G is 6.67 times 10 to the negative 11. The M1, which is 90 kilogram. M2 is 60 kilogram. And then we have R squared, which is 2 here squared. So it's going to be 2 squared. Let me just write it as 2 squared for now. I know it's equal to 4. And there we go. So what I want to do now, I want to use a calculator to get a number out of that, okay? So, and I think in a previous video, I showed you how, which calculators and how to use the calculator to write specifically scientific notation. There is a neat little calculator on your computer if you are a Mac user or a Windows user. It's kind of a local, it comes with the software, and I'm currently using a PC, a Windows operating system, and there is I think it's called Microsoft Calculator. You can look it up on the you know, on the search field, and it's called Microsoft Calculator. You go to the Microsoft app or store, whatever it's called, the App Store, there we go, and you download it for free. It's a free calculator, but it's a wonderful calculator. Here it is. Sometimes I use it if I don't have my calculator with me, my handheld calculator, that is. And it allows you, look at this, it allows you to, there is a standard calculator, which is just basic things. And then there is the scientific calculator, which is a little bit more sophisticated. It got just about everything you need. One of my favorite buttons is this one, the FE. I don't even know what F and E stand for, but I'm going to show you in a minute why this button is useful. It has also, can I make it bigger? I wonder. Oh, okay, I can make it bigger. There we go. Okay, good. Let me just brag about it a little bit. So basically, it allows you to, to write any equation. It will calculate for you. The button EXP is for, it allows you to write the number in scientific notation. This EXP, I think it stands for exponential. I'll come back to it in a sec. And then there are powers. So for example, if you want to square something, you just push the button X squared. For example, let's say I have 5 right here. So when you, let me go back. So the display is right there on the top. So if I go 5, it will just go there. Square becomes 25, just like that. You see what I'm saying? You can erase that. And then let's say 5. I want to take the square root of it. This is the square root right there. And you will get, whoa, you get this huge number of digits that are totally useless for us. All you need to do is you just get the number to the left of the decimal point, and then basically 2 digits after the decimal point. That should be good enough in most cases. For our case here, it will be 2.24. Remember, there's a 6 here, so when you round it, it becomes a 4. So, and then you just ignore the rest of them, okay? I don't know if we can reduce those number of digits, but this Microsoft calculator gives you lots and lots of digits that you don't need. So make sure that you don't want to write all of them. Just put in, like I said, 2 digits after the decimal point. So anyway, that's how it is. This also, let me delete it. The pi value is right there. Again, it gives you a huge number. All you need is just the first 2 digits after the decimal, 3.14, and so on, okay? So let's go back to our calculation. So I want to use this calculator, try to reduce it as much as I can. I'm working within a screen that There we go. Oh, now it's disappeared. Do it again. There it is. Okay. So what I want to do, I want to type in this the formula, the numbers that I have in the equation. I want to input them into or enter them into the calculator. So we begin with the universal gravitational constant. So 6 point. Oops, I think I am not. Hold on. There we go. I wanna show you the display. So let me go back. Let me just trash everything. There we go. Okay. So we have 6.67, right? And then there is times 10 to the power of negative 11, correct? So times 10 to the power, all of that, okay? The time and the 10 is basically exp. Once you put exp, see that e right there? That means times 10 to the power. You don't need to type in 10 or to the power or raise it up, okay? And then there is a minus here. So now if you look at the right side of it, there are the 4 binary operation: division, multiplication, subtraction, and addition. This is not a minus sign. This is a subtraction sign, okay? The minus sign is right here. See this? Plus and minus. If you look at this plus right there, look, I can toggle it, toggle between plus and minus. See? Minus, plus, and so on. So I want the minus, so you put it in minus, and then I'm going to put 11, 1, 1, and there we go. So this number, 6.67 times 10 to the power negative 11, equals to 6.67 e negative 11. So remember, the e here means times 10 to the power of. You got that? Anyway, so we have that. Now I'm going to multiply by 90 and then 60. So times 90 equals, always put an equal whenever you do one binary operation, times 60 equal, and we got that. Still not a very pretty number. It's fine. Divided by 2 squared, divided by 4. But let's just make it 2 squared, okay? So divided by, and what you do, because it's a squared, I have a parenthesis here. So you click, I already made the division right there. See the division right there? So I'm going to open up the parentheses, this one. And once you open it, you'll see that number 1 right there. It's telling you that the parenthesis is open. It's right there. It's open, and it's ready to put in. Ready for you to put some number in there. Okay. So I'm going to put a 2 just like that, and then I'm going to close the parentheses. You see what I'm saying? And I'm going to hold on. I think I want to go back. Let me go back to this. There we go. I want to open it up. I am not sure if I go 2 squared, there we go, and then close the parentheses, there we go. So you want to put 2 squared, that's a 4, and then equal to, and that will give me my number. Okay. Okay, the next step now is to convert this into scientific notation. You see what I'm saying? I mean, you don't write this huge number. It looks pretty ugly. Now, from your previous video, that I created, and from your previous knowledge, we can convert the standard number into scientific notation. And the way we do it, let me do it first manually, and then I'll show you how to use the calculator for that. It's just one push of a button. So what you do, you move the decimal point all the way to the very first digit, which is right, the 9. So I'm going to put it right here between the 9 and the 0 here. So I'm going to count the number of steps. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so my prediction is going to be 9.00545 right there, times 10 to the negative 8 because I moved to the right. You see what I'm saying? So let's see if I'm right. So all you need to do is you take this FE button right there. It will immediately convert it into scientific notation. And there we go. So it's going to be 9.0045 E negative 8. What that means is, let me go back to my So go back to my formula, and that's equal to, I forgot what the number is, sorry, what is it? 9, as you can see here, we want to put only 2 digits after the decimal, so basically 9.00 times 10 to the negative 8. So 9.00 times 10 to the negative 8 Newton. And there we go. Okay? So now let's look at this number. How big is it? As you can see, this number is extremely small. This one basically telling us it's 900 millionth of a Newton. Okay, it's really, really small. So small that you can basically neglect it. It's not trivial, almost zero. Okay, what I'm trying to say is that Newton's gravitational law, this formula right here, the force law, okay, it's really insignificant in our daily lives because the gravitational pull by its own nature is a weak force. As a matter of fact, it's so weak, you know, let me explain it to you. When you stand up on the floor, okay, stand up on the ground right now, you can actually jump off the floor. What that means is that the muscles in your legs are actually stronger than the gravitational pull of the earth. You see what I'm saying? When the idea of you climbing, say, a tree or a wall, you are actually overcoming this gravitational pull. The muscles in your body is actually stronger than this giant earth that is underneath you. Okay, so why is it important? Well, it's important only at the astronomical level. In other words, this formula is extremely important at the astronomical level. In other words, when the mass here is extremely large, like the mass of the earth, mass of Jupiter, mass of the sun, and so on, the force here becomes significant. But in our daily life, look at that number. It's totally insignificant, and that's why we never calculate it. It's just not important. Okay? So now I want to apply the same formula, and now this time, however, we want to use, terrestrial bodies. So, for example, what is the gravitational pull between the Earth and the Sun, for example? Okay? So let's do that. So that would be my last example for this video. So gravitational pull, between the Earth. The symbol of Earth is a circle with a cross in the middle of it, kind of a cool symbol, and the Sun. And the symbol of the Sun is a circle with a dot. You've probably seen it before. And the symbol of the Moon is basically a circle. So the mass of the Moon, we say M with a big circle like that. That's mass of the Moon. This is mass of the Earth. And this is mass of the Sun. Okay? Kind of a cool symbols in astronomy. I'm not sure what the origin of them, but anyway, you can look it up. So anyway, let's see. So if I put in my formula, so we have here the force is equal to G, M for Earth, M for the Sun, divided by the distance between the Earth and the Sun squared, right? That's basically the formula that we're going to use. And I want to show you how big the number is and how significant this force F is at the astronomical level. All right. So what I need now, I need data. I need the mass of the Earth. I need the mass of the Sun and the distance between the Earth and the Sun. Now we can go back to either your book, you can go to Google and just put in something like the mass of the Earth, or you can go back to the formula sheet. Let me show them to you on the formula sheet first. So go back to your formula sheet. If I were you, I would download it and put it in your desktop so it's always handy. You can always look it up. So in the formula sheet right here, look at right there. So at the bottom right here, you have Earth mass right there, roughly 6 times 10 to the 24. And the Earth radius, the Sun radius, there we go, the mass of the Sun is 2 times 10 to the 30 kilogram. The distance, excuse me, between the Earth and the Sun is it's a unit that we're going to study. It's called astronomical unit, AU. And just 1 AU is the distance between the Earth and the Sun. And there it is right there. AU is 1.5 times 10 to the 11 meters. Okay, so we got all these numbers right there in the formula sheet. Okay, another option, let me just take it out. We can go to the web. Let me go to the web for you. Oh, I already did that. Here we go. The distance between the Earth and the Sun is this large distance right there. Of course, you have to convert it into scientific notation. It boils down to what I have just showed you, 1.5 times 10 to 11. Okay. We can also look up, say, mass of the Sun right there, and it is equal. I guess he gives you more precise values right there. Roughly 2, 1.989, that's almost 2 times 10 to the 30. Mass of the Earth is given to you is right there in kilograms. Okay. Now, if you want it in let's say a different unit, you can just put in that unit in there. Let's say in grams, for example. We don't use them in grams, but yeah, if you want it, there we go. Okay, and so on. So you can just put in the unit explicitly. Google will understand that and immediately give you the value in proper units. You know what I mean? Okay. So let's go back to the formula. So let's plug in all of that number, all of these. So I have the force. The force F is equal to 6.67 times 10 to the negative 11. Please don't just look at the screen and watch me. Please grab your calculator and calculate this with me, because a lot of students make mistakes when they are entering numbers into the equation. What I'm trying to say is that a lot of you would use the right equation, the right steps, and then some of you would make a mistake only in the calculation. So you have to develop a skill for using your calculator, whichever calculator you want to use, whether it's a handheld regular calculator, the one I recommended for you in a previous video, or the calculator that you have on your cell phone. That'll be fine if you can download one of those in your phone. I know some people are comfortable with the phone. I'm old school. I like a calculator, handheld or the one on my PC. Whichever, but make sure that you are familiar with one and stick with it, and so you will avoid making mistakes. Anyway, moving on. So the mass of the Earth, as you know, is forgot what it is. What is it? I want the precise value of it. Mass of the Earth, 624. Let's just say 624. So 6 times 10 to the 24 kilogram. Mass of the Sun is 2 times 10 to the 30. Let me make sure I am doing it right. Oops, not this one. Where am I? Mass of the Sun, 2/30ths, that's right. And then the distance between them is 1.5 times 10 to 11 quantity squared. You see what I'm saying? And there we go. So how do we enter all of that? Okay, here's how you do it. So what I want to do, I want to bring in my calculator. I want to show you I want to bring in the online calculator, the one on my PC. I want to move the screen down there because the calculator is going to take up some space here. There we go. Maybe I'll make it a little smaller. Sorry, bear with me. There we go. Okay. I mean, this is 10 to the 30, so let's just remember that. Okay, so we start with the universal gravitational constant, 6.67 exp negative 11 negative. Unfortunately, I want to show you what's going on here. So negative 11. There we go. I am done with this part. Now I'm going to multiply by the mass of the Earth times 6 exp 24 equals. Again, always put that equal in there. Whenever you do a binary operation, just make it equal, and then multiplied by the mass of the Sun. It's hidden, but it is 230. So it is 2 exp 30 divided by, and we get this number. Okay, so this is basically the numerator for this equation. Okay, 8 it's written in scientific notation, it's 8 times 10 to the 44. Now, I would like to, just to be careful without making any mistakes, because I don't want to make mistakes, I want to write down this number. So basically what I have gotten so far is, go back to this one, 8 times 10 to the 44, and of course I'm dividing it by this number right here, so 1.5 times 10 to 11 squared. So let's continue on with this. So I'm going to take this number, I'm going to divide it by, see that there's a division right here, divided by, and then I'm going to open up my parentheses, 1.5 exp 11 squared, excuse me, close the parentheses, squared, and then equal to, and that will give me the answer right there. Okay, so what I've done, I divided this number 8 times 10 to the 44 divided by 1.5 to the power of 11 quantity squared, and then that will give me this number right here. This number, I think I've done it correctly because it looks familiar to me. I've done it before. So again, you want to ignore all these crazy figures that you have here. Many of them are not significant at all. So basically, you want to take 2 digits after the decimal to the right of the decimal. So that will be 3.56 times 10 to the 22 right there. You see what I'm saying? I mean, if you want it in the standard number, it's like right there, there's no way you can read this number. It is absolutely crazy. So anyway, so the number that I have, 3.5622. So that's equal to F equal 3.56 times 10 to the 22 Newton, and that's the final answer. Now look at this number. Look how big this number is. You can't even read that number. I mean, a trillion is a 12 here. The power of a trillion is a 12. Okay, this one is 22. That's almost trillion Newton. Now compare this with the gravitational force between two people. 10 to the negative 8, totally insignificant. But look at the gravitational pull. Now, this force, this big number, is actually the one that is responsible for moving the Earth around the sun. Can you believe it? So the Earth goes around the sun because of a force, the gravitational force. How big is this force? It's this one, 3.56 times 10 to the 22 Newton. You see what I'm saying? So again, let me just, the last comment that I want to make is, make sure that you understand the fact that Newton's gravitational law is an important law as long as you are dealing with astronomical object, big, massive object. But at the small level, it becomes insignificant. Okay? Okay. You have a wonderful day. Bye-bye.